What specific problem does your method of analyzing dormant attention heads aim to solve within the context of large language models, LLMs? Could you elaborate on why understanding these dormant heads is significant in deep learning?
Our method of analyzing dormant attention heads aims to address the issue of identifying attention heads in large language models, LLMs, that contribute minimally to the model's output, thereby allowing for potential model optimization without sacrificing performance. Specifically, we propose a formal definition of dormant attention heads, termed honor, which quantifies head outputs based on their contribution relative to other heads in the same layer. Understanding these dormant heads is significant because it enables efficient inference by identifying heads that can be zeroed out without degrading model accuracy, as demonstrated in our model intervention studies across multiple benchmark datasets. This insight not only aids in reducing computational costs, but also enhances our understanding of the attention mechanism's behavior, particularly how certain heads can become inactive or dormant during training. Ultimately, this knowledge can inform future strategies for model pruning and optimization, leading to more efficient deployment of LLMs.
How does the proposed method for identifying dormant attention heads, defined using the honor metric, work? Please illustrate this step by step, including the key components and calculations involved in the process.
The proposed method for identifying dormant attention heads using the honor metric involves several key steps and calculations. First, the method defines a dormant attention head at the head level, meaning that if a head is classified as dormant, it is considered dormant for all tokens in the sequence. The identification process begins by calculating the output of each attention head, denoted as text head_I, which is a matrix representing the head's contributions across the input sequence. Next, the average norm of the outputs for each head is computed using the formula text average norm t equals frac1 n sum_I equals 0 caret n t_I_2, where t is the output matrix of the heads. The honor metric then classifies a head as dormant if its average output norm is below a specified threshold, tau. For example, if tau equals 0, 1, any head with an output norm less than 10% of the average norm of all heads in the same layer is considered dormant. This systematic approach allows for the identification of heads that contribute minimally to the model's output, thereby facilitating efficient inference by potentially zeroing out these dormant heads without significantly impacting model performance.
Can you provide a simple example that illustrates the detection of dormant attention heads using your proposed honor metric? Please walk through the example, detailing how the measurements are taken and interpreted.
To illustrate the detection of dormant attention heads using the honor metric, consider a transformer model with multiple attention heads. For a specific input sequence, we compute the output of each attention head, denoted as head_I, which is a matrix of size n times d_verses. The honor metric calculates the average norm of these outputs across all heads in the same layer, defined as average norm t equals frac1 n sum_I equals 0 caret n t_I_2. If the average norm of a specific head's output is below a defined threshold, tau, e.g., tau equals 0, 1, that head is classified as dormant. For instance, if we find that the output norms of heads head_1, head_2, and head_3 are 0, 0.5, 0.15, and 0.08 respectively, and the average norm across all heads is 0, 1, then head_1 and head_3 would be identified as dormant since their outputs are less than 10% of the average norm. This detection indicates that these heads contribute minimally to the model's output, allowing for potential pruning or zeroing out without significantly affecting model performance.
What are the main theoretical and practical benefits of identifying dormant attention heads in pre-trained models? How does your approach compare to existing methods in terms of efficiency and accuracy?
Identifying dormant attention heads in pre-trained models offers both theoretical and practical benefits. Theoretically, it enhances our understanding of the attention mechanism by revealing which heads contribute minimally to model outputs, thereby refining our comprehension of model behavior during pre-training. Practically, our approach allows for the zeroing out of these dormant heads without compromising model accuracy, as demonstrated by our model intervention studies across multiple benchmark datasets, where over 14% of heads can be zeroed while maintaining performance. In comparison to existing methods, such as the first token approach, our method, Honor, is more efficient, as it does not require tuning specific thresholds for different models and datasets, and it consistently identifies unimportant heads across various contexts. This efficiency in identifying dormant heads can lead to potential applications in dynamic attention head pruning and KV cache reduction, ultimately improving inference efficiency in large language models.
How did you validate the effectiveness of your method for identifying dormant attention heads? What specific datasets, benchmarks, and metrics were used in your experiments?
To validate the effectiveness of our method for identifying dormant attention heads, we conducted model intervention experiments using multiple choice benchmarks, HelloSwag, WinoGrande, ARC Challenge, and MMLU, as well as the open-ended generation task on GSM-8K. We measured the impact of zeroing out dormant head outputs on model accuracy across these datasets. The primary metrics used in our analysis included the percent of dormant heads, which quantifies the fraction of heads identified as dormant for a given input, and the percent of heads zeroed, which is equivalent to the average dormant heads across the datasets. Our results indicated that using the Honor method allowed us to zero out over 4% of a model's heads while maintaining accuracy, demonstrating its effectiveness compared to the first token method, which required more tuning and was less consistent across models. This comprehensive evaluation across diverse datasets and metrics confirmed the robustness of our dormant head identification approach.
What limitations or drawbacks did you encounter with your proposed method for identifying dormant attention heads? Are there specific scenarios where this method may not perform as expected?
One limitation of our proposed method, Honor, for identifying dormant attention heads is that it requires computing the output of each attention head, which may not be feasible for head pruning since it necessitates a forward pass through the model. Additionally, the method identifies different dormant heads for every input sequence, making it less straightforward to apply uniformly across various contexts. Another drawback is that while Honor effectively identifies unimportant heads, it may not account for the specific behaviors of models with varying attention sync patterns, as seen with OLMO 2-11247b, where a different threshold would need to be tuned for optimal performance. Furthermore, our analysis indicates that the effectiveness of Honor can vary based on the input characteristics, such as the complexity and structure of the text, which may lead to inconsistent identification of dormant heads. Lastly, while Honor generally performs well, it may not capture all nuances of attention head activity, particularly in cases where heads transition between dormant and active states during training.